Well, hello and welcome back to our mini review series. Our first topic is limits. So go ahead and take some good notes here, and we'll be looking for them in class tomorrow. So first and foremost, always try first substitution. Many times, just taking the limit you're approaching and substituting it in actually will give you an answer. If that fails, your second option is to factor. Third would be to use the conjugate method if you have a radical. And fourth, you can use the L'Hopital's rule if and only if you have that indeterminate form, which is 0 over 0. Now, I just want to be clear, back in that substitution method, if you get 0 over a number, that's okay, then your answer is clearly 0. And if you get a number over 0, that's okay too, your answer is does not exist. The only time we're using the L'Hopital's is if we get 0 over 0. All right, example number 1. The limit as x approaches 5 of x squared minus 24 over 5 minus x. So again, try direct substitution first. 5 squared should be 25 minus 24 all over 5 minus 5. So on top I get 1 over 0, and since this is not 0 over 0, I can't jump to L'Hopital's rule. My answer is done here, and the limit just does not exist. Okay, limit does not exist. Number 2, I see a nice radical, and I'm going to try to plug 11 in first. And if I plug 11 in, direct substitution, I've got 4 minus 4, which is 0 over 0. So I could use L'Hopital rules, or I could use the conjugate method. And I'm going to try the conjugate method. And you're just rationalizing wherever the radical is. So since it's in the numerator, I'm rationalizing the numerator. X plus 5 plus 4 over the square root of x plus 5 plus 4. So remember, you multiply by the conjugate. I'm not actually going to waste my time multiplying the bottom. I'm just going to write down what I get. X minus 11 times the square root of x plus 5 plus 4. And on top, I am going to FOIL this out. Remember, any radical times itself is just that junk, so I get x plus 5. And then I'm going to get a positive 4 radical x plus 5, negative 4 radical x plus 5. They cancel every time you use the conjugate method. And then, of course, minus 16. And now, if you clean up the top there, you'll notice you'll get x minus 11. And then this should happen every time. These should cancel if you did it correctly. So you basically have 1 over the square root of x plus 5 plus 4. Now, you're not done until you plug your limit in as x approaches 11. So I've got 1 over the square root of 16 is 4 plus 4 should be 8. And hopefully a nice easy 1/8. Now again, you could have used L'Hopital's rule. Just take your time there. Carefully take the derivative of the top and bottom. And I'll go ahead and squeeze that in blue up here. I'll try to write as neat as I can. The derivative of the top would be 1/2. That x plus 5 to the negative 1/2. Derivative of the inside is times 1 minus the 0 all over 1. So if I were to rewrite that, that would give me 1 over 2 square root of x plus 5. And again, plug in your 11, and you should get the same answer as 1/8. So whatever method you prefer works fine. Question 3. The limit as x approaches negative 1 of z cubed, as z approaches negative 1 of z cubed plus 1 over z plus 1. So again, carefully plug in your negative 1. Negative 1 cubed is negative 1 plus 1 should be 0 over 0. So because I get that, of course that's telling me L'Hopital's rule. And I just want to be clear, if you do L'Hopital's once and it doesn't give you a finite answer, you can repeat L'Hopital's until you get an answer. All right, repeat as many times as you need. And L'Hopital's just said take the derivative of the top. So I should still have the limit as z approaches negative 1. On top, I'm going to get 3z squared all over 1. And if I plug in my negative 1, I'm going to get negative 1 squared is 1 times 3 all over 1. I should get an answer of 3. All right, moving on. Limits as x approaches infinity. All right, so this time when you see a limit as x approaches infinity, you need to think power fight. And there's 3 options that can happen in your power fight. You will get an answer of 0 if you have small over large. You'll use the ratio of the coefficients when you have the same over same. And you'll get it does not exist. Now the AP doesn't always say DNE. A lot of times they'll either use positive or negative infinity, so you have to take your time to determine which one that is. And that's if you get large over small. Now, keep in mind that implies that you have a slant asymptote. Okay? All right, so the big deal that you need to remember here is unless you know your answer is 0, you must plug infinity in to determine the sign, whether you're getting a positive or negative infinity symbol, basically. So let's try a few examples. All right, example number 1. The second I see that limit as x approaches infinity, I'm looking for my power fight. So basically, I'm finding the biggest power on top, and then everything else means nothing. Find the biggest power on the bottom, take that sign with it, and everything else means nothing. And now I just compare my exponents. I have a 2 on top, a 3 on the bottom, so I would say that's small over large, which automatically is 0. So I don't need to worry about whether that term's positive or negative, because I already know my answer is 0, and 0 doesn't carry a sign. Let's try another one. Number 2, I tried to squeeze in here. A little different. The limit as x approaches negative infinity of sine theta over theta. All right, so picture this. The trig functions are always a little sneaky. If you picture the sine curve, the largest it ever reaches is 1, and the smallest value it ever reaches is -1, compared to plugging any number in for theta down here. So the sine curve is obviously from -1 to 1 is a very small range, so I would say that's small over large, which again is 0. Number 3. Limit as x approaches negative infinity of x to the 4th minus 36 over 2x squared minus 10. So grab that power fight. Largest guy is x to the 4th. This means nothing. Largest guy is 2x squared. This means nothing. I would say I have a large over small. Now, remember, this is where it gets a little sneaky. Your answer can either be does not exist or plus or minus infinity. And again, the AP is probably going to go with the plus or minus infinity. Now you have to determine whether you're positive or negative infinity. So, very simple. All you have to do is plug negative infinity in to determine whether you're positive or negative. Well, what is negative infinity to the 4th? Just the sign, positive or negative. I would definitely say anything to the 4th is a positive value. Plug negative infinity in on the bottom here. Negative infinity squared again is going to be a positive value. So this is going to be a positive infinity. All right, so the biggest mistake people make is not checking the sign whether to see if you actually have positive or negative infinity. So don't fall for that. Number 4, compare your largest terms. So my largest is negative x cubed over 2x squared. I've got large over small again. All right, so again, that's either positive or negative infinity. I just have to determine which one it is. So if I plug negative infinity on the bottom, negative infinity squared is a positive. And then if I plug it in on top, positive infinity cubed is positive, but there's a negative out front. Therefore, this answer is going to be negative infinity. All right, last limit as x approaches negative infinity. So again, I'm going power fight. I'm going to kill this and this. So my biggest term is negative 3x cubed and negative 4x cubed. So since the coefficients are the same, I think ratio of the coefficients. Now I'm just going to check the signs to determine whether I'm positive or negative. If I plug negative infinity in on top, negative infinity cubed is a negative times a negative 3 makes that a positive. And if I plug negative infinity on the bottom, negative infinity cubed is a negative times a negative 4, which makes that a positive. So I can say I get a positive 3/4. I think by far the hardest type of limit are limits similar to the definition of the derivative. All right, and I think as a whole, this is the one where we struggle with the most. So if it's similar to the definition of the derivative, it looks like that definition, the limit as h approaches 0 of f of x plus h minus f of x all over h. And here's a great example of it. Okay, so here's f of x plus h minus f of x all over h. Now, I would probably just start by, again, direct substitution. And if I plug 0 in, I'm going to get the tangent of pi over 4 minus the tangent of pi over 4, 0 over 0. So I am actually going to jump straight to L'Hopital's rule. So I'm going to use the derivative of tangent, which is secant squared. Keep the inside. The derivative of the inside, well, the derivative of pi over 4 is 0 because it's a constant and the derivative of h is just 1, minus the derivative of the tangent of pi over 4. Remember, that's just a constant. Tangent of 45 is 1. Its derivative is 0, all over 1. And lastly, just make sure you substitute in h approaches 0. So I get the secant squared of pi over 4, all over 1. Secant squared of 45, so I'm thinking cosine of 45 is radical 2 over 2. So if I flip that, I get 2 over radical 2. And then, of course, secant squared. So I would say that's 4 over 2, or just 2. Now, that's typically easier than the next example I'm going to show you. The limit as h approaches 0, and again, it's in that form, f of x plus h minus f of x all over h. Now, again, this is probably the most common one. Please make a note here. There are two variables in the problem. There's x's and h's, but you're going to take the variable that the limit has. So the only variable you're treating is h. Okay, so h is the variable, and x is going to be treated like a constant. That is the key. H is the variable, x is the constant. So when I plug 0 in, I get the ln of 2x minus the ln of 2x over h. There's my 0 over 0. So I'm going to use L'Hopital's rule, but keep in mind, h is the variable, x is the constant. So right away, I'm going to cross this off because I know its derivative is going to be 0, since x is a constant. So the derivative of an ln is du over u. My u is 2x plus h. The derivative, remember this is a constant, so its derivative of h is just 1. And then of course all over 1. Now I can plug in my h approaches 0, and I get 1 over 2x. So be very careful. Like I said, that is the toughest problem. Pause it, replay it if you have to. H is going to be treated like the variable, where x is the constant. All right, let me give you another example. The limit as h approaches 0 of x plus h cubed minus x cubed all over h. So again, if I were to plug 0 into h, that's what it says here, I would get x cubed minus x cubed over 0, 0 over 0. We can go L'Hopital's. So again, this is getting treated as the variable. The x is going to be treated like a constant. So the derivative of x cubed is actually going to be 0. So when I take this derivative, I'm going to get 3, keep the inside, raised to the second, and now I need to take the derivative of the inside. Well, remember, x is a constant, and the derivative of h, because that's taking the variable place, the derivative of a variable is 1, all over 1. Now I can plug my 0 into the letter h, and I simply get 3x squared. All right, our last little piece is limits graphically. And the whole key to solving limits graphically is to ask yourself, what is the intended height of the function? Not what does it actually reach, but what are its intentions? Where does it plan to get to? So if you just kind of quickly copy this sketch down as best you can here, we're just going to talk about whether the limit exists or does not exist. So at A, and actually before I should go on, let me scroll up here. The definition of a limit, the one that you're going to have to repeat on your quizzes and tests, is the limit as x approaches a from the left of f of x has to equal the limit as x approaches a from the right of f of x. Okay, the left side has to equal the right side. Some of you miss the notation. Make sure you have a function f of x or g of x, whatever your function may be, but it's got to look just like that. In order for a limit to exist, the limit from the left equals the limit from the right. So if I scroll back here and I look at A, from the left-hand side, A looks like it's getting to a height of 2. From the right-hand side, A looks like it's getting to a height of 2. So I would say the limit exists, and the limit as x approaches A of this function f of x equals 2. The limit exists. Now, if I asked you what was f of a, certainly you wouldn't tell me f of a. F of a is actually 4. Its actual height is 4. But it's intending to reach a height of 2. All right, let's look at B. From the left, it looks like a shooting up towards positive infinity, and from the right, a shooting up towards positive infinity. However, does the limit exist? The limit as x approaches b of f of x actually does not exist. even though they're both headed in the same direction, they're headed towards infinity. Infinity is not an actual tangible number. So my answer is does not exist. Okay, but our whole key is the limit from the left has to equal the limit from the right, and your limit exists. Well, I hope that was a quick review on limits, and I look forward to seeing you tomorrow.